Bien, buena tarde a todos. Gracias nuevamente por estar. Sí. Gracias por estar nuevamente aquí con nosotros. Vamos a la última parte del día de hoy, en donde está programada la presentación de Scott. Pero antes quiere aquí dar James una pequeña presentación y hablar algunos detalles que se comentaron anteriormente. Entonces, por favor. Gracias.
Thank you. I just want to take 5 to 10 minutes to give you the latest from NOAA on the ABI cooling system anomaly that's due to the loop heat pipe. Dr. Volz, our director of our satellite service, gave a press conference this morning, and some information has been put on the website. I believe that we've covered all this already, but I just want to give you the latest information that's available. And you can find this on the NOAA NESDIS website under press. So the link is up above. Okay. So Dr. Volz said this morning that the ABI has experienced technical issues with its cooling system during the orbital checkout phase of GO-17's 6 instruments. The other 5 instruments are performing normally. The cooling system is a significant part of the ABI and did not start up properly. There's a fact sheet that you can download that I'll review with you now, and also the audio is available as well. Pam Sullivan is noted here as our director. I want to mention that Pam is our new director of the GOES-R program, and she was previously the flight project manager, has been with the GOES-R program for quite a while, and she's an outstanding director. We're happy to have her taking charge. So I'll just read some of this here. Let's see. Okay. So the role of the ABI loop heat pipe is to keep the ABI at the correct operating temperatures. The ABI infrared detectors need to be cold to accurately measure the thermal energy radiated from the Earth's atmosphere. The detectors need to be cooled to varying degrees, some as low as minus 351 degrees Fahrenheit, based on where they fall on the electromagnetic spectrum to function properly. The ABI has different ways to maintain thermal control. The mechanical cooler pumps heat away from the visible and infrared detectors to cool them to their required temperatures. The heat is transported to an external radiator by the loop heat pipes. The radiator is a large reflective surface designed to reject excess thermal energy to space. The blankets and shields protect the instrument from absorbing too much solar radiation. Sorry. So the loop heat pipes transfer excess thermal energy to the radiator. If the loop heat pipes are not operating correctly, then the cryocooler and other electronics get too warm and have to be turned off to prevent them from being damaged. Experts are investigating the cause of the issue and pursuing several possible corrective actions. Based on their efforts, the ABI is showing improved performance. The experts are working to improve channel availability and adjustments in operating procedures, software, and algorithm changes. They have also narrowed down the number of possible root causes to a few likely possibilities. A series of ground-based tests is underway to isolate the specific root cause. Additionally, design modifications for the GOES-T and GOES-U ABIs are being explored to ensure the cooling system issue is not repeated. Okay, thank you. Are there any questions? We just want to make sure you have the latest information since we're here, and thank you very much.
Of course, I saw something on that had nothing to do with the loop heat pipe. So NOAA 20 day-night band imagery over Athens. I don't know if you heard, there's tremendous fire to the south of Athens going on, killing people. We have the fires are here, and here are the city lights of Athens. So kind of a difficult time for the people of Greece right now. Okay. Okay, just want to first start off with a big thanks to the people in the back in the booth who are doing the translation. Now I'm reminded of something, this will challenge them. College basketball in the U.S. is pretty big, and the Wisconsin team went to the end of your tournament a while ago, and the team members there were taken by the stenographers who have the steno machines, those small little typewriters that convert what you're saying into phonemes. But then they would throw out these really long words just to stump the stenographers, like onomatopoeia or cattywampus or sesquipedalian. So I hope I gave some words to challenge the translators for you. So make sure you thank the translators when you leave here because they're doing a great job. Okay, this is the best part of my job, is I get to look at beautiful imagery. I don't think I need to listen to the translation while I'm talking. So every day I get to go in and look at satellite imagery. So I'm looking at ABI all the time. It's great to see. It is so beautiful. So I'm really thrilled to be able to come here and talk to you about it because everyone should be as excited about this data as I am. So we'll talk about some practical applications today and some tomorrow as well. Thank you to some people. Most of these people are people I work with. Bill Line, again, is at the National Weather Service in Pueblo, Colorado. The other people on the list are in the same building as I am. And a lot of people worked to get this data flowing to you. Thankfully, it did not have the loop heat pipe problems as badly as GOES 17 has. So we can see the data. And every day I see something awesome, and I'm just blown away. So thank you. Okay. Right now, GOES 16 is GOES East, and GOES 15 is GOES West. And for everybody in this audience, GOES 16 is providing better spatial resolution. So that yellow line at 120 West, this is where, to the west of here, GOES 15 has better spatial resolution. And of course, GOES 16 has better temporal resolution. GOES 16 has better spectral resolution. It's better. Everything about it is better. So as it says, GOES 16 has better spatial resolution than over all of Central and South America. So you might still be using GOES 15 to look at stuff out in the middle of the Pacific. But for everyday things, I think it's better to use GOES 16 because you have better spatial resolution. Now when GOES 17 becomes operational, let's say best case everything ends up working. I'm not sure if that'll happen. Best case, then the dividing line between better better spatial resolution between GOES 16 to the east and GOES 17 to the west is at 106 degrees west longitude. So again, most of Mexico's Central and South America will be using GOES 16 with its better spatial resolution, and only the northwestern part of Mexico and of Baja would have better resolution from GOES 17. Some things to ponder as I go through this. You know, there's 16 channels on the ABI. You might ask, well, why do they put those all on there? I mean, I did my job perfectly well with just the visible and the infrared. But there are lots of reasons why you might want to start thinking more multispectrally. So I just have land surfaces at 0.86 microns, which is one of the channels, are more reflective than at 0.64 microns. There's an application there over on the right. Ice clouds at 1.6 microns, and I'll be going over all this later in more detail during the next 60, 90 minutes. Ice clouds are more reflective at 0.64 than at 1.6. Multiple water vapor channels mean you're seeing different levels into the atmosphere with water vapor. And we have different amounts of water vapor absorption in these window channels. So you can use the differences between those two to differentiate where you might have low-level moisture increasing. Or for these two channels, you can also use them to detect dust. So lots of reasons to have all these different channels. I think you've seen a similar image to this, 5 times the scanning, 4 times spatial resolution, and 3 times more spectral bands. So 60 times at least more data that you're getting. And there's someone standing next to the ABI there, just to show you the size of it. So we have 16 channels. So this is from GOES 16 when it was in the test position at 89.5. So we have the 2 visible, 0.47 and 0.64, 4 in the near infrared or near visible, either way you can say it, 0.86 microns, 1.37, 1.6, 2.2. Then we have the near infrared, the shortwave infrared at 3.9, the 3 water vapors at 6.2, 6.9, 7.3. Then we have the longer wavelengths, including the window channel at 10.3. Now the question is, am I going to use these every day, all the time, making forecasts? Probably not. That would overwhelm people. So which would you use routinely? Well, I've grayed out ones that you might not use routinely. For example, the 13.3 micron, the CO2 channel is on GOES 13. How many of you have been using that operationally routinely? It's there mostly for product generation. 2.2 microns is a cloud phase distinction, cloud particle size distinction in the near infrared. It's also used for fires, but 1.6 does a lot of what 2.2 does, and as we'll see, 1.6 has higher spatial resolution. So why use 2.2 when 1.6 does it? And then we have this window channel 11.2 that's kind of duplicated by 10.3, and the ozone channel at 9.6. So just because there's 16 channels, don't feel an obligation because NOAA is giving you all this data to look at all the data. Use your best judgment about which ones are going to be useful for your problem of the day. So here we have just the table form where we have the central wavelength on the left. The ones that are in bold, it's hard to tell, but 0.64 is in bold, 3, 9, 6, 2, 11, 2, and 13, 3. Those are similar enough to the legacy GOES 15 and GOES 13 that I've bolded them. And then we have whether it's visible, near infrared, or infrared. The nickname. So these nicknames were developed by a forecaster in the National Weather Service. That's a great idea. Thank you. So I don't know if it was developed kind of on a lark, but it was just developed as something a shorthand to describe to describe some of the functions. Of course, it's not describing all the functions. Best spatial resolution, this is in kilometers. So 0.64 has the best resolution, half kilometer. That's at the subsatellite point at 075.2. Of course, as you move away from there, you get into the resolution degrades a little bit. So maybe in northwest Mexico, instead of half a kilometer, you might be looking at 1 kilometer in that particular band. Then we have some other attributes of the different bands on the right-hand side. I like this chart, and I show it a lot. It takes some explaining. So we have the 10 infrared bands, 7, 8, 9, 10 to 16, and then we have wavelengths along the bottom here. These blue regions are the spectral response function, so this is where the satellite is detecting energy at these different wavelengths. The red line is what a satellite would detect, the temperature the satellite would detect above, if you had a satellite sensing uniformly over all of these wavelengths at very small discrete intervals, these are the temperatures that would be detected assuming a US standard atmosphere. So that has a particular moisture and temperature distribution. So if you're down here near the bottom, around 290 Kelvin, so these brightness temperatures are in Kelvin, around 290 Kelvin, you're sensing the temperature of the surface, and it's a window channel. So you're seeing through the atmosphere all the way down to the surface. And you'll notice there's these three channels, 8, 9, and 10, at 6.2, 6.9, and 7.3 have a much cooler temperature because energy at this wavelength that leaves the surface is absorbed by water vapor and then re-emitted from a colder temperature. And eventually it gets up to a region of the atmosphere where there's no more water vapor above it, and it escapes out to space where it's detected by the satellite. So you're detecting a colder temperature from higher in the atmosphere because water vapor lower in the atmosphere is absorbing energy from down low. So here we have the 3 water vapor channels. You'll notice 8.4 here has a lot of absorption spikes. These are related to both water vapor and sulfur dioxide. So it's an important channel for volcanic detection. Here we have the ozone channel where there's a lot of absorption due to ozone in the stratosphere. And the CO2 channel at the end here. So there are a couple of regions that aren't detected. There's a big CO2 detection, an interesting CO2 detection region around 4.5 to 5 microns. There's detection for that with the GOES sounder that's on GOES 13, 14, and 15, but it's not on the ABI. So if you're looking for temperature in the mid-troposphere, you can get a little bit of it from the 13.3 microns, but the GOES sounder did a much better job of sensing mid-tropospheric temperature because it was sensing in this region of CO2 absorption. So this is a chart that shows the brightness temperature difference due to various atmospheric components. So you have a completely, you have an atmosphere that's composed of only nitrogen, oxygen, and argon. And then you start adding gases and then subtracting the brightness temperatures. And so here you see the cooling that's due to water vapor. It occurs everywhere. Water vapor really has an effect on every channel. In the green, we have the effects due to CO2, and you'll notice they're up at pretty long wavelengths, around 13 microns and up, and also around 4.5 microns. So if you remove the CO2, you have changes in the temperature. There are also other ones for ozone, sulfur dioxide, carbon monoxide, methane. So they all have different absorption spikes in different regions. But really the ABI was only designed for ozone, water vapor, and SO2, not for these other trace gases. You would need something like CRIS on NOAA 20 or SUMI NPP to detect these other trace gases. Because the CRIS does have observations uniformly across this entire spectrum. So here's that same chart. I might have flipped it, nope, it's the same chart. So this is in the infrared. On the top we have what's going on in the visible, and this gray line that's pretty hard to see is showing you the transmittance. So for example, in bands 1, 2, and 3, and 5, and 6, transmittance is pretty close to 1. So energy that's being reflected, or energy at that wavelength, is transmitting right through the atmosphere. The unusual channel is at 1.38. You'll notice the transmittance drops down to 0. This is in a region of very strong water vapor absorption in the atmosphere. So energy from the sun at 1.38 microns comes into the atmosphere and it's absorbed. So it's not available to be reflected. So as soon as you have water vapor, you lose a signal in the 1.38. So if you look at the 1.38, and we'll see some examples in a bit, you really only see high clouds because once it gets lower into the atmosphere, the water vapors absorb the entire signal. This is a matrix that we've been putting together if you have some kind of phenomena that you're looking for. So for example, dust or burn scars or smoke or snow cover. What channel do you use? There are 16 different channels. And this is just a recommendation of, okay, if I'm looking at burn scars, what channel do I use? And you use the veggie channel, the 0.86 microns, because it's very sensitive to how green the surface is. If you have vegetation, the veggie band is very reflective. If you don't, it's not as reflective. So this is a handy little chart that we've distributed to the Weather Service to help their forecasters. So all these arrows here for the 11.2 is like, well, if you ever use the 10.7, which is very similar to the 11.2, use the 10.3 instead. Okay, this is just first slide. This is a slide you might have seen before, just showing the CONUS domain for ABI in the test position at 89.5. So it was about a year ago. No, more than a year ago, January of 2017, a long, long time ago now in satellite time. It's much, I say it's much better looking now. So there were some problems in some of the bands at this time because this is preliminary and non-operational. Although I don't label it as such, which I should have done. Luckily, it zoomed out enough that you can't see the problems. So what kind of bands are those? Those are just shown here. So we have visible in the upper left, the blue and the red bands, near infrared and a phase channel. Then we have window channels here, and the water vapor channels, 8, 9, and 10, ozone and CO2. So I'm just going to I'm going to go through most of the bands, not all of them. Maybe I'll give you a quiz at the end to say which ones did I skip. Oops, went the wrong way. Oh, I didn't know that worked for this too. So for visible data, old goes 13 and 15. I guess goes 15 is still present goes. It's just I don't know. Substandard's not quite the right word, but deficient. How's that? GOES 15 has one band at 1 kilometer. Now with GOES-R ABI, you have one band at half kilometer, the 0.64, and one band at 1 kilometer. So better resolution of cloud features. Boundaries show up very nicely. It's easier to monitor smoke and aerosols, and you can produce true color imagery because you have a red and a blue. Red plus blue plus green makes true color. And I'll also add, the better resolution is also, what I'm not talking about here when I'm talking about you have better spatial resolution, now you have 5-minute imagery instead of 15-minute imagery too. That's huge. So the blue band, this is in a part of the electromagnetic spectrum where scattering is important. So this is the transmittance, and you notice as you go from the red band, band 2, 0.64, to the blue band, 0.47, the amount of transmittance is dropping off as scattering is increasing. So scattering is preferential in the atmosphere for smaller wavelengths. So with 0.47, it's easier to see aerosols, especially by comparing what you're seeing at 0.64 and 0.47. So it's a good way to determine whether there are aerosols, be it smoke, dust, haze, that kind of thing in the atmosphere. One problem with the blue band, can't use it at night. It's not a day-night band, it's just a daytime band. And it's got 1 kilometer resolution. That's not a limitation though, that's a feature. So here's an example. This is using AHI data from the Japanese satellite because it's so good. It's such a great example of a smoke pall over Siberia. So this is all smoke. You know it's smoke. Let's see. Because if you look at 3.9, you'd see hot spots all over the place. So there's stuff burning. So you have this smoke pall, and this shows up so much cleaner or so much more distinctly in 0.47 than in 0.64. Now, I don't have a lot of Himawari examples, but the AHI imager and the ABI imager, I would say, are first cousins. AHI has the same channels as ABI, except AHI has a green channel at 0.51 microns that ABI does not have. But ABI has the 1.37 Cirrus channel, which I really like. That's not why they have it, that AHI does not have. Now in 2019 or 2020, the Koreans will be launching AMI, which is also very similar to this. AMI will have the green band 0.51 and the 1.37, but it will not have the 2.25. So there'll be 3 different satellites up there with very similar imagers, with just some tweaks in the visible and the near infrared. So here's an example using ABI. So here's smoke over northern Mexico. Shows up very nicely in the blue band and the 0.47, but I can't see it in the red band, even though it's a higher spatial resolution, or in the veggie band, or in the 1.38 really. So sometimes smoke or dust will show up in this shorter wavelength, 0.47, because there's more scattering, and the detector is more sensitive to that. One thing I've noticed, if you look at a shadow, notice how the shadow is very distinct at 1.61, a little less at 0.86, a little less at 0.64, and you really can't see it all at 0.47. So just in case you were wondering, does scattering really exist in the atmosphere? Yes, it does, because this shadow is not distinct because light is being scattered into it on the path length to the satellite. So just something I like to look at. I see this every day when the sun is coming up. Really, really dark shadows in the snow ice channel 1.61. Not much shadow at all in the 0.47. Okay, band 2 is you're probably all familiar with. But it's much better on GOES 16 because it's got better resolution. So the uses you would use for GOES to the 0.64 in the legacy GOES are the same ones you'll use in GOES 16. So much better temporal resolution. So this is not something you could do with, I don't know why there's that black one at the end. I guess it hadn't quite loaded when I made the animation. So this is just showing at 5-minute steps how well it captures the convective initiation down here along the Mexican Gulf Coast. So this is 20 north right here. I'm not sure what states these are, but you know exactly where the overshooting tops are. You can time this convective initiation, maybe down to the 2.5 minutes or 5 minutes. If you put a mesoscale sector over there, of course, you could do it down to the minute. I can look at this kind of animation all day. There were no near-infrared channels on the current GOES. So GOES 13 and 15 and 14 don't have any channels. There are 4 near-infrared on the ABI. 2 have 1 kilometer resolution, 2 have 2 kilometer resolution. Some of these channels have been around. So for example, AVHRR has a 0.86 and a 1.61. MODIS has these channels on it, and so does VIIRS. So these aren't new, except they're new to geostationary. So benefits to the operational meteorologists are listed here. And I'll show you some examples. So band 3 is the veggie band. As I said, this is on AVHRR, so it's something you might be familiar with if you have used polar data. 1 kilometer resolution. Vegetation, this is very reflective. So this is an important part of true color imagery. This is where the green comes from when you want to make a red, green, blue true color. And I'll explain that in a bit. So why does this work? Well, this is the the spectral response function. So this is what's being detected by the red, 0.64, and this is what's being detected by the 0.86. And superimposed upon that is reflectance above green grass. So you'll notice green grass is not very reflective in the visible. There's this little bump at 0.55. This is why, for example, MODIS has a channel at 0.55, because there's this peak in reflectance there, not at 0.51. And VIIRS also has a 0.55. And you'll notice dirt is not super reflective. If you ever noticed imagery, dirt is brighter than green grass in the 0.64. But look what happens when you get beyond 0.7. There's this huge increase in the reflectance over green grass or vegetation, and there's this steady increase in dirt. So vegetated land is a lot brighter in the 0.86. So I'm just cycling through. This is visible, the 0.64 and the veggie band, and I hope you can see why you might want to use the veggie band if you want to see exactly where the land sea boundary is. I'm kind of curious what's going on in here, where it's kind of an intermediate reflectance. I imagine there's even a flood. It's either a marshland or it's flooded, one of the two. Maybe it's a tidal plain, I'm not sure. Wetland, okay. Oh, mangroves. Okay, but if you're like looking for islands, they show up in the 0.86. They don't show up in the 0.64. One thing that's kind of a problem in the 0.86 is the land's so bright, it can get hard to see clouds. So there's great contrast in the visible between the dark land and the clouds, but there's not great contrast in the veggie band between the pretty bright clouds, the pretty bright land and the very bright clouds. So, choose the one you're using correctly, or make a judicious choice in which one you're using. Now, if you're in an island region, if you're in the Caribbean, sometimes it's pretty hard to see the islands in the visible, but they will always show up very nicely in the veggie band. So if your area of responsibility includes islands and you want to know exactly where they are, the veggie band is what to use. Veggie band is also very useful for burn scars. So this is a before and after, nicely vegetated. You get a burn scar on top of that though, and suddenly it's dark. This is important in regions where there are burns if you want to monitor where you might have flash flood potential, because nothing is going to impede. If this is mountainous terrain, I'm not sure if it is, it's close, but if this is mountainous terrain, rain is not going to be impeded by any kind of vegetation there, and it'll just run right off and you'll have mudslides and flash floods. Whereas if it was falling here on mostly vegetated surfaces, you're more likely to have less of a chance of a mudslide. The only challenge with this is you kind of have to know what your surface typically looks like before their fire. You can use it to monitor the fire burn scars, but you have to know what the vegetation looked like beforehand, because this could just have been a difference in vegetation. So maybe this was, if I just showed you this, it's not clear if that's a burn scar or just a difference in vegetation, except you can also see smoke plume. So here's an RGB image that was created using variations in green. So there are variations in green here, even though there isn't a green band on GO16. So what they've done is taken some of that reflectance in the veggie band, not all of it because there's too much of it, and they've used it to create a green band so they can make an RGB image. Now there are other ways to process. Let's see if there are other ways to do processing here. If you're familiar, for example, with the Sierra GeoColor, that has also removed Rayleigh scattering from the scene, so it looks a lot more vivid. They like to say it's what it looks like from space, but that's false because there is Rayleigh scattering. If you're out in space, your vision is being affected by the signal from the Earth is being affected by Rayleigh scattering. So this is just a strict combination without the Rayleigh scattering removed, so it's a bit more muted. But you see the nice differences in color over different regions. This is great, by the way, for tracking smoke, blowing dust, because they all have different colors. If you're tracking something with different colors, like smoke or blowing dust, it'll show up very well in the RGB, in the true color, pseudo true color imagery. Okay, one of my favorite channels, 1.38. Now you might ask, why did they put in 1.38 when they could have put in 0.51 to have a green band? And the answer is that if you look at the blue band, the green band, and the red band, they're all very highly correlated because the signals are all very similar. But the 1.38 is really uncorrelated from just about everything because it's affected by water vapor. So it's giving you a unique signal that, in my opinion, means it's more important than the green band. So again, this is a region where there's very strong absorption by water vapor. So here's the transmittance through the atmosphere, drops down to 0. So if there's moisture in the atmosphere, you don't see the surface, but you'll see anything reflective above the water vapor. So cirrus clouds show up great with this, which is why they call it the cirrus band. If you have a very dry atmosphere and you have dust in it, dust is also highly reflective at 1.38, so you can see dust with the 1.38 band. So anything that's above the water vapor, you will see. And there might not be any water vapor if it's a very dry atmosphere. Again, this is 2-kilometer resolution. So here's a picture of Harvey. I was going to say Hugo, but that was wrong. Hurricane Harvey from last year. This is the cirrus channel. You'll notice you don't see any feeder bands over the Gulf of Mexico. Very moist there. So if all you're interested in is what's going on in the cirrus canopy above the storm, the cirrus channel is what you want to use. You can also see the cirrus with all the convection over the surrounding continent. You can see dust. You can see blowing smoke in the cirrus channel. So this is an example from up over Maine. So we have this plume of smoke from Canadian forest fires that's being entrained into this circulation system. Now you might ask yourself, well, how do I know that's not cirrus? Because cirrus could be doing this as well. And you would have to look at some other channels to make sure that that's actually smoke you're looking at and not some kind of upper level cloud feature. So you have 16 channels. If you have a question, look at a different channel, you'll probably get the answer. Here's just another example. This is actually using MODIS data. As I said, this has been on MODIS, and this is on VIIRS for a long time. So here we have the visible image here, and here we have the cirrus channel. You'll notice these low clouds. It's very hard to see them because most of the information has been absorbed as the sunlight has been reflected off of that. So there's enough water vapor above these clouds that you can't see the signal at low levels. And then the cirrus shows up very nicely. So it's a good way to discriminate between regions of high and low clouds. Okay, this is another of my favorite bands. You probably are wondering how many favorites I have. Well, I have 2 kids, and I have 2 favorites for kids, so I can have more than one favorite band. This is the nickname of the Snow Ice Band. This is also on AVHRR, 1-kilometer resolution, also has good land-water contrast. But the thing you use this for is discriminating between ice clouds and water clouds mostly, or snow on the ground and water clouds above, as we saw an example for that earlier. We saw an example of that before lunch. So here we're looking at the 2 visible, the 0.47, the blue band, the 0.64, the red band. Here we have the 0.86, 1.38, 1.61. What I want you to focus on is the reflectance here of snow and ice. Very highly reflective. Snow is highly reflective in the visible. It's highly reflective in the veggie band, but then it drops down to almost nothing in the 1.61. So what's happening here is snow is absorbing this energy. It will not reflect it. So you have a very dark signal in both the 1.6 and the 2.2. So here's another example from Himawari that I really like because it's a nice extratropical cyclone out over Kuroshio to the east of Japan. Look at the nice cirrus shield here. Shows up very nicely as dark. And then we have lower clouds here, lower water-based clouds. You can also see lower water-based clouds near the surface circulation. And if you look at this closely, you can see the individual thunderstorms growing up along this cold front and then glaciating. So that's one really nice thing about the snow ice channel. A storm starts out with water droplets. It's very highly reflective in the 1.61. As soon as it glaciates, it loses that reflectance and they become dark. So it's a really nice way to say, okay, which of these thunderstorms that I'm looking at have glaciated? If you have the 1.61, the ones that have glaciated are dark. So here's the quiz. Here we have a visible image. Just glancing at that, how many glaciated clouds do you see? And to make it easy, I'll show you the 1.61 is here. It'd be nice if they were not, it looks like they're moving. But there's one here that's pretty obvious, glaciated. This one. And there's some down in here too. I have a hard time doing this. It looks like this one. I have a hard time doing this over water because the, oops, or near land surfaces because the land is changing. Now there's also a product. There are lots of GOES products that have been developed where where the computer is doing the work for you and it's saying, okay, if they're green here, they're glaciated. No, that's not right. If they're red here, they're glaciated. So this one up here that was very obvious, glaciated. Here we have some green that's supercooled water, but a lot of the signal down here is showing up to be water. Here's an example where you might use this without clouds on the ground, in the surface. I don't know how often. I was happy to see the example of snow on the ground in northwest Mexico earlier because I wasn't sure how pertinent this example would be. But this is over the southeast part of the US. And there's a snow band here, and you know it is snow because when you look at the 1.61, it's dark. So it's absorbing the energy. And it's even more interesting than that. If you look over this region, so here's the snow on the ground in the 0.64. And if I toggle between the two of them, that region in the green box is actually even darker. So there's a dark signal here with the snow, and this is even darker. This is actually freezing rain and sleet on the ground. So it's differentiating between what kind of ice is on the ground, whether it's snow crystals or sleet and freezing rain. And I know that's the case because the National Weather Service in Tallahassee tweeted out this image saying, here's the ice along the coastal plain, and here's the snow that's just inland, and that's what you see in this particular image here. So here's the freezing rain on the coastal plain with snow just inland. And then if I step back to the visible, you see exactly where the snow is. So I don't know how frequently that'll be used in Mexico. I don't know how often freezing rain happens down here. Not here, I'm imagining, but up in northwest Mexico. But it's just a nice example showing the kind of the power of the 1.61. This is one of the reasons it's one of my favorite bands. So here we have an example of the same scene where it's a very complicated scene. So we have snow on the ground here. You can kind of tell the topography is showing up. But look at the difference in the white here versus down here. We have cirrus clouds that are showing up in the 1.38, and they're showing up as darker in the 1.61. And then we have mid-level clouds here that are not really showing up in the 1.38. They're fairly bright here. So even though they look these clouds all have the same kind of reflectance in the visible, again, the 1.61 can differentiate between the cirrus clouds, which are dark, and the clouds that are comprised mostly of water, which are a little bit brighter. And you might even want to use the window channel to get the temperature of them. As I said, the GOES veggie and snow ice channels can highlight floods. This is just showing, this is over the state of Missouri during some flooding, and it shows the blue band, which is on the screen now, then the red band, which has higher resolution. Now here we have the veggie band, and then the snow ice channels after that. So you really can see inundation. So if you have a case where there's flooding and it's clear, you can really see where the horizontal extent of the flooding is occurring. And you can even do this when it's mostly cloudy if the clouds are moving. So I saw a really nice example of this after Harvey, they were looking at very quick animation, so the clouds are moving very quickly, but in the background, because they were using the 0.86, you could see the regions that were flooded. And they even inferred some inferred some flow from one basin to the next that they weren't expecting during the flooding of Harvey around Houston. Okay, switching to the infrared. So the current GOES has 4 bands in the infrared, and the GOES 16 has 10. Much, much better. So one of the things that I really notice is the better precision of it. The images look so much cleaner. If you look at the 10.3 on GOES 16 versus the 10.7, even though the resolution is, you've gone to 2 kilometers, all the edges look very crisp. So I think there's a much lower signal to noise ratio with the current GOES. So some benefits listed here. So the kind of the unique band in the infrared is the 3.9, the shortwave infrared, unique because it has a signal both from the emitted signal from the Earth and also reflected signal from the sun during the day. So it's used for a whole bunch of different purposes. It's got 2 kilometer resolution. You can use it for fire detection. I'll be talking in depth about this tomorrow. Cloud phase determination because ice crystals have different scattering properties at 3.9 microns based on their size. Emissivity properties of water-based clouds differ between 3.9 and 10.3, so you can use it to detect fog at night and other things. So here's just this is preliminary non-operational. So this is from last March, just combining here. This is southerly winds, so I'm guessing there's some kind of moisture coming up off the Gulf of Mexico. All you would see would be the cirrus coming in from the west. In fact, I should make that image. That would be kind of cool to see it. The temporal refresh of GOES 16 is important because you can use it to determine exactly how things are changing. This is a mesoscale, so this is 1 minute imagery. So you can see how the fire is changing every minute. So this is a fairly famous example from last March also. So we have very hot spots here. It's kind of hard to see in this image, in the 3.9, but you will see a somewhat brighter enhancements as the cold front comes down. And you'll see as the cold front intersects this region, it flares up, and then the direction of the motion changes. So I think the cold air is getting there about now. So you'll notice things start going in a different direction. I'll show you this one a little bit later as well. But because you have it, potentially have data every 1 minute, it really helps to monitor how a fire is spreading. It's also very sensitive. This is a case, again, from Bill Line, where this is this circle is in the middle of nowhere in Colorado. And they were able to say there's a fire in this place, and they sent the information to the emergency responders so they could get there early. So there have been cases in Oklahoma, for example, where there's an automated system where finds a hot spot, pings what would be 911, and the signal gets there before any 911 calls happen. So it's a really great way to monitor clouds. And I'm not sure if this is 1 minute data or 5 minute data, but either way gives you a great way to detect what's going on, because your eye is really, the human eye is great for seeing changes, and that changes pretty quickly, and your eye is drawn to it. You could also color enhance it to bring out some color there. Fires are also detected in the other shortwave, in the other near-infrared 1.6 and 2.2. As the fire gets hotter and hotter, you get more and more energy from the shorter and shorter wavelengths. So it's pretty easy to see a fire in 3.9 microns. As the fire gets hotter, a signal will start in 2.2, and the super hot fires will show up in 1.6 as well. So here's that other example, and I have the 2.2 down here, and you notice how the reflectance is increasing in the region where you have the fires. So this was, there are wildfires everywhere. Please do not throw your cigarette butts out the window. I don't know if that's the cause of any of these fires or not, but a lot of these fires are caused, I think, by sparking with high tension wires get blown together. They shower sparks and a fire ensues. You can also combine the 3.9, the 2.2, and the 1.6, and you can make this RGB product that shows up red where you have a fire. And then if the fire gets even hotter, you get some 2.2, so the red turns into yellow. And if it gets hotter still, you get a contribution from the 1.6, which is the blue. So red fires are probably kind of run-of-the-mill. If you saw any, I don't think there are any yellow or white fires in here. So a very hot fire would be glowing white, would be showing up as white. So this is called the fire temperature RGB. So they're RGBs that you can use to create an alert. So this is, I think this is good situational awareness because that red kind of pops. I mean, if you've got some kind of color deficiency, some red, green, blue color blindness, it'll be harder to see it, but for someone without that color deficiency, this is a good way for situational awareness. There are also baseline products for fire that I'll be talking about tomorrow. So you can see some pixels showing up here as fires have been detected. 3.9 is useful for detecting fog, and that's related to emissivity. A water-based cloud it emits radiation at all wavelengths. It does not emit 3.9 micron radiation as a black body. It does emit longer wavelength radiation as a black body. The satellite, of course, is just up there detecting photons. So it's detecting these photons at 3.9 microns, and then it makes a temperature out of that, out of the amount of radiation it detects. And that inversion from the number of photons back to a temperature is assuming whatever is emitting this energy has done it as a black body. So if you are not emitting as a black body, then I would say not enough photons have been detected for that temperature. So the inversion gives you a cooler temperature. So you see these regions where you have water-based clouds. You see these regions where you have water-based clouds. 3.9 microns is not emitting as a black body. So the temperature, the black body temperature that's computed, assuming a black body emission, is too cold at 3.9. So you take a difference between the two, and you have a very strong signal over clouds that are made up of water droplets. So here we have a, oops. And then where you have cirrus, you have something else called the subpixel effect. If you have a cloud that is not completely covering an entire pixel, the 3.9 micron is more sensitive to the warm part of that pixel. The 10.3 is more sensitive to the cold part. The 3.9 micron is more sensitive to the warm part of the pixel. That's why you can use it to detect fires. So basically what happens is a sign changes. So the 10.7 is showing colder temperatures because in this thin cirrus, it's more sensitive to the coldest part of the pixels. Well, you can use this part here to detect low clouds at night, which is shown here. So here I have an example where we have, in this enhancement, this blue region is all low clouds. And you'll notice there's a region in here where you have low clouds indicated where you might not expect low clouds to happen in the summer. I don't think there's a big concentration of fog commonly happening in July up in the Colorado River Delta. And if you look at the visible imagery, a couple hours later, you notice you just see sand down there. So what you need to know is that emissivity differences that are driving this, you also have emissivity differences based on soil type. So you can have a false signal of fog here because the soil is not emitting as a black body. So you just need to know the surface you're looking at. Now, going to the water vapor, we have three. So these are the spectral response functions for band 8 at 6.19, band 9 at 7.0, and band 10 at 7.3. And this red line, this is the spectral response function for GOES 13 or 15. I'm not sure which. They're pretty similar. And one thing you'll notice is how broad GOES, the old GOES has, whereas now you have these three separate locations, three separate water vapor channels. And what do the three separate water channels get you? You get information at different levels. So this band 8 at 6.19 microns, this is typically looking high up in the atmosphere. You usually don't see the you usually don't see the surface with this channel, so it's not usually a window channel. You can see the surface sometimes in very dry air masses over, for example, mountains. You'll see mountains peeking through. Or if you're in the Great Lakes in the middle of winter and it's super cold and super dry, you might see the outlines of the Great Lakes. So the level that this information is coming from is variable, and that depends on both moisture and temperature. And so you might ask yourself, well, how can I tell? And there are weighting functions that can be computed to identify exactly where that information is coming from. So then band 9 is a little bit lower in the atmosphere, and band 10, 7.34, is a low-level water vapor channel. So you can see lower down into the atmosphere with 7.34 than you can with a 6.19. 7.34 is also sensitive to sulfur dioxide. So you can use that to, it has some information when volcanoes occur. So I said, how can you tell where the information is coming from? And for that, use weighting function. So there's a website here that you can play around with this if you're stuck in traffic, for example. So you just choose your band, choose your atmosphere. There are a couple choices: a zenith angle, column moisture, and a skin temperature adjustment. So I won't be going through all of these. And then you hit go. So what I've chosen here is just a zenith. We're at the subsatellite point. Zenith angle is 0. Column moisture is 100%. So we're looking at a standard tropical atmosphere, and we haven't reduced any of the moisture. And we're looking at the three channels. And here's what we have. We have a weighting function with band 8, 6.2 microns, has a peak around 330 millibars. And band 10 has a peak around 530 millibars. So the information from band 7 is coming from lower in the atmosphere. So the moisture controls where it's coming from. So here we have the images that I just showed you in the bottom slide. I put them up. So it's band 8, 9, and 10, 6.2, 6.9, and 7.3. Standard tropical atmosphere, so it's pretty moist, 39.36 millimeters of total precipitable water. And you'll see as you get longer and longer wavelengths, you're getting information from farther and farther down in the atmosphere. Here we have a mid-latitude summer atmosphere, and I've taken out 80% of the moisture, so it's much drier. And you will notice right away that the information is coming from much lower in the atmosphere. So 6.2 microns, it's coming from around 500 millibars. 7.3 microns, it's coming from 700 millibars. And you're even getting a signal at the bottom here from the surface in the 7.3 microns. So you dry out the atmosphere, the water vapor sees farther down into the atmosphere. So you really need to know how moist is the atmosphere and what's the temperature to know exactly where that information in the water vapor channel is coming from. And it's three-dimensional. You can do this with real-time weighting functions. There's a website here. This now includes Mexican stations. They're listed here. The difficulty is that sometimes the data doesn't flow from Mexico to the US in time. So that's something we're working on. But you can use this to find a weighting function. So this is, again, just the mid-latitude summer atmosphere, very dry, and again, seeing information all the way down to the surface. Standard tropical, kind of the same thing, but we're not getting information from the surface in the standard tropical because there's more moisture there. So again, the energy is leaving the surface. As it goes up, it's absorbed by water vapor. 7.3, as I said, is also affected by SO2. So this is the brightness temperature difference due to SO2. So we can have absorption by SO2 in band 10 and also in band 11. So if you have a strong emission of SO2 from a volcano, it'll show up nicely in GOES 16. Unfortunately, GOES 16 cannot see Kilauea. There'd be a great signal if it was able to see that, because there has been some significant sulfur dioxide emitted from Kilauea. So water vapor in the tropics, I just put this one in here because I thought this was interesting. You don't really see this low-level boundary that's propagating to the west in the 7.3. So the 7.3 is seeing farther down in the atmosphere, and you'll notice on one side of this boundary there's a lot of convection, on the other side there's really not very much. So this is some kind of drying feature that shows up in the 7.3 microns that isn't really showing up in the 6.2 or the 6.9. So because you have these three different layers, seeing three different channels, seeing at three different layers in the atmosphere, make sure you make use of that, because you might see something in one layer that is not showing up in the others. This is another use for mid-level water vapor. So this is a case of strong downslope winds, and you'll notice there's this one small region of very bright red here where there's the strongest subsidence, and that was associated with the most severe turbulence. This is very close to Denver Airport, which is down here. So they had a ground stop there while they had this region of very strong downward motion, as inferred from this mid-level water vapor. Oops. This is Irma. And one thing that the water vapor does a nice job of doing is showing the beginnings of extratropical transition. So we have this nice dry punch coming down, interacting with the system as it starts to become extratropical. So great animation. And this is looking at 6.95, channel 9. You could do this at 6.2 or 7.3 as well, but I just chose this one. This is one just showing how at 7.3, this signal from Mount Pavlov in the Aleutians, so this is Himawari imagery, is a lot colder in 7.3 because of the extra SO2 absorption. I'm skipping a couple bands now to getting to 10.3. This is called the clean window. So if you used the 10.7, this does the same thing. It does it better. So there are 4 window channels on ABI. These are the 4 channels: 8.4, 10.3, 11.2, and 12.3, or by band number 11, 13, 14, 15. So this one has SO2 in it. So if there was an SO2 event, you might want to use the 8.4 to see that. But otherwise, 10.3 is giving you the best signal, the best view of what's going on near the surface, because there's the least amount of water vapor absorption. So you use it to monitor systems. So here's Irma crawling along the north coast of Cuba. So it looked fairly similar in the 11.2 and the 12.3 and the 8.4. But again, this is just a little bit cleaner imagery because there's less water vapor absorption in this channel. And again, much cleaner look. So this is a CONUS over Canada, and you're seeing all these surface features show up very distinctly because of the fine precision of the 10.3 micron. So why do you have so many IR channels? Well, that's because if you take the difference between them, you get information. So I mentioned the 10.3 minus 12.3 gives you information about moisture with one sign and dust with the other. 11.2 minus 8.4 tells you something about ice crystal size. 3.9 minus 10.3 gives you low-level stratus at night and updraft strength. And you also have these products that rely on the different IR channels. So the 11.2 micron is used in a lot of products. You might not necessarily use it operationally unless you're using those products, but that's why it's there. So the baseline products are shown here. Of course, more information at www.gosr.gov. These are the baseline level 2 products. So these are the ones that are being put out first, and then there's a follow-on series that's scheduled for at some point. So I could talk on all of these as well, but then we'd be here a long time. I'm showing you this again. So this is for AHI. So it's a little bit different from ABI. So ABI has 0.47 and 0.64. AHI has this channel. ABI has that one. So this is just the spectral response function for AHI. So notice 1.38, that real nice valley in the transmittance. It's not being sensed by AHI, but they do have something in the green part of the electromagnetic spectrum. Just a quick comment on bit depth. Data from the legacy GOES 13 and 15 were 8 bits. So 256 different values. GOES 16's channel 7, the 3.9 micron, has 14 bits. So that's almost 17,000 discrete values. So you get much finer precision. So make sure if you're using a color table that it's created to take advantage of all this extra bit depth. There are quick guides on all of these channels if you want to learn more. So those are at gosr.gov. There's also, I've created new ones that use only GOES 16 data. So these fact sheets were created before launch. So then I was told, well, we have data now, why don't we put those in the fact sheets? So there are new ones out there. So just some concluding remarks. This is really a huge improvement to the imagery. I haven't talked about how it scans, but you know that mode 3 is 5-minute CONUS imagery, simultaneous with a full disk every 15 minutes and the mesoscale sectors. And mode 6, which I hope will happen, will have 10-minute full disks. Now, if you're wondering about your data volume with the mode 6, I would just ask you, what do you do with mode 4, which is full disk every 5 minutes, which doesn't happen very often. But it is that's the highest data flow rate with GOES 16 is mode 4, continuous full disk. Some useful links. I really like this one that Tim Schmidt puts together. So if you go to that one, you will see it's his link of link pages. So again, I'll slip back. So this is the one that has links to just about everything related to GOES 16 that Tim knows about, and he's been working on GOES 16 longer than anybody else in NOAA, active in NOAA. Other people have retired. There are blogs that talk about GOES 16 data. Here's some quick guides. So the new quick guides are at this particular link, which talk about GOES-R channels and products and channel differences. And there are also these quick briefs, not a lot of them yet, short videos on GOES-R products and differences, and you can go there and learn about the split window difference, for example. Again, Tim's handy dandy. If you want to learn about training and education, find imagery, find ways to display imagery, it's all there. There are two journal articles. This is one from 2017. Here's a more recent one from 2018. This one's online at this particular website, where we basically just said, okay, you've got 16 bands, what do you use them for? So I think that's all. Yep. I'll be happy to take questions as soon as I put on my... So I didn't really talk about the 9.6, which is ozone, or the 13.3, or the 8.5, which is important for volcanoes, or the 2.2. Those were the 4 that I mostly glossed over. Okay, someone get... I'm looking for someone with a microphone.
in the Spanish. Sorry. Perdón. Creo que es una pequeña omisión en una de sus tablas cuando habla de incendios, porque no marca la banda 14, que es muy importante para incendios. Yes.
Right. The question was, if you're looking for fires, for fire products, it typically compares what's going on in band 7, the 3.9, and band 14, the 11.2, and I'll be talking about that tomorrow. So, because I have a fire presentation tomorrow.
Gracias por su presentación, primero que nada. Una pregunta, esto es para interés del Servicio Meteorológico Aeronáutico. Voy a consultar mis notas. En la banda 7 de 3.9, según esto es una ventana en el shortwave, en el infrarrojo. Pero hay también una en 10.3, hay otra ventana o clean window, y está en el máximo de radiación infrarroja de la Tierra. 3.9 es, creo yo, menos radiación. Sin embargo, en la otra tabla que había, se habla de que es una de las mejores para detectar niebla. ¿Podría haber algún comentario al respecto, por favor? Detectar niebla sobre agua.
Yes, that's a particular challenge. One of the nice things about detecting fog over land is you lose all the variability in this surface topography, so you can kind of tell if it's a cloud or not. And when you have low clouds and fog over the ocean, the challenge there is discriminating between whether it's a stratus cloud or if it's reaching all the way down to the surface as fog. That's a big challenge using only satellite data. There are fused data products that have been developed. Mike Pavlonis at NOAA has done this, where he has an IFR probability field that combines the emissivity of 3.9 and 10.3, so it's to determine whether or not there's a stratus cloud. And then in addition to that, it's looking at rapid refresh data near the US or GFS data outside of the Northern Hemisphere, really, to say, does the model expect saturation here? And if those two things are true, that if it's a stratus cloud and the model says it's saturated, then you have a very high probability of IFR conditions. Using only the satellite imagery is a challenge because the satellite just sees what's going on at the top. The top of a stratus cloud looks a lot like the top of a fog bank because they're both water-based clouds. So you need something to give you information about the cloud base, and that's what the model data does. And you can find that, I think, online, IFR probability.
¿Hay alguna otra pregunta en relación a este tema que acabamos de ver? Bueno, no veo ninguna. Entonces, un aplauso, por favor, para Scott.
Thank you. And I have to say that on my revision of this, I had another image that I'm going to find online and show because I really like it. Okay. I hope it's on here. You have to cross your eyes. So this is created using, let let me load up the animated GIF that keeps going instead of the MP4 that stops. It's kind of big, so it'll take a while. So this is an animated GIF using GOES 16 data on the left and GOES 17 data on the right. So you cross your eyes until you see 3 images, and then you focus on the one in the middle, and that's in 3 dimensions. I love making these. Because you really do see the 3 dimensions in the clouds. So if it's something you have to learn how to do. But then when it finally works, it's like, wow. So can people see 3 dimensions? Okay, I see one person nodding their head, so success. So this is something we learned as an undergrad. I had a professor who loved this. So if you did not learn this as an undergrad in meteorology, well. So again, cross your eyes until you see 3 images, focus on the one in the middle, and then bring that one into focus. So I'm either wowing you or frustrating you.
Did the students that couldn't do that fail?
I don't remember. That was more than 10 years ago. This works best if you're actually in between GOES 16 and GOES 17, so somewhere between 75.2 and 89.5. But it still works here at, what, 100 and, this is what, 109 west, something like that? Keep trying.
Ok, so, perdón, pues muchas gracias a todos. Pues muchas gracias. Con esto damos concluida nuestra segunda sesión del taller GOES 16. Mañana ya concluimos con este tema. Aproximadamente planeamos tomarnos el mismo tiempo que nos tomó hoy, o sea que estamos cortando un poco el tiempo del taller. Sin embargo, se están agotando y estamos dando todos y cada uno de los temas conforme lo hemos acordado inicialmente en el programa. Igual el esquema mañana, la comida. El jueves ya cambia el taller. Son nuestros mismos colegas, por supuesto, quienes estarán dando esto, pero ahora el tema está enfocado no en el GOES 16, sino en el sistema GNC. Entonces esperamos contar con su participación y muchísimas gracias por su interés y por su presencia. Que tengan buena tarde y nos vemos mañana. Hasta luego. Listo, mi G's. Muchísimas gracias. Muchísimas gracias por ustedes. Sí. Qué bueno. Estamos ¿ya? Por favor, por supuesto. Sí. Pero al personal de ellos no. A lo mejor en alguno de también se ve. Sí, no realizar por nosotros. Coincidimos, probablemente. Quizás para